Hi guys, today I wanted to talk to you about the parallel configuration of a buck converter. You basically have to put the parallel switches like this, parallel switch buck converter, and this will make sure that your converter can sustain more amps than a classical converter. There is also the multi-phase configuration, which is basically creating more phases from the same input voltage like this. And you can even use the two configuration altogether, so, namely multi-phase and parallel. I will discuss the multi-phase in another video, but for now let us focus on the problem of the parallel switch configuration. Let us call here Q1, Q2, Q3 and Q4. So you may think that the current in Q1 and the current in Q4 are the same, and it is I over 2. This is what you think. In reality, in the transient and so on, there can be some possible current mismatch. As you can see in this paper, you have the same configuration that I draw here of a buck converter, and let us call this Q1 and Q3. The name is different, but you got the picture. So basically, if here there are some stray inductance which are different from the position of the layout, you're gonna have different current in the transient and maybe even in the steady state. So the current here is the ID1, and as you can see, it spikes up to 10 amps. And instead the other one, IQ3, has a very low current flowing. So meaning that the current which is flowing here can be very dangerous. We can see this in LTSPICE by using the buck converter. So let us use dot param d. Let me take for instance this, and let me use these two pulses. These are just the two square wave. So I can run this, but honestly, these are just the two square waves, as you may see. So I just took dot param dd equal to 200 nano, and let me use the dead time, because in this video I want to calculate the efficiency. Okay, maybe this dead time is a little bit higher. Let me increase the switching frequency to 50 kHz. This is even worse. Okay, so let me keep it to 250. Okay, so now let us draw the buck converter as always. Let me clean a bit. So this will be 10 volts. Let me use this as V in, and let me use the classical MOSFET. G1, and S1. Let us pick the first MOSFET on the list. And let's use the other gate, G2 and G2. So now we have the 4 MOSFET in parallel, and let us put the inductor here, or 4.7 micro, and a bank of capacitor with a reasonable ESR. This should be enough. And let us put the load of 10 amps. So now we should be fine. Let us put even a resistor here of 1 milli, just to simulate the effect of the ESR of the inductor. So I think that we can run the simulation. I don't want to skip the transient at first, because I want to see everything. So let me see everything for the first time. Okay, there is this strange oscillation which honestly I can't explain why this is happening. Let me... But if the final result is correct, so if I can have Vin times 0.25, yes, there is the dead time. Let me put the dead time to 0. So okay, I think that with a little bit of ripple, we are near the result. So we need to have a transient of at least 10 milli. Sorry, 5 milli. I think that it is enough, so that when we are calculating the efficiency, we are not somehow... let me put 6, should be better. Okay, so now we have just the classical ripple, and I think that we are fine. Let us put the duty cycle to 0.552, so that we take into account also the dead time between the two, and I think that we should have 5 volts. Sorry, 250 nano. Sorry, 250 nano. Sorry, my bad. We should have a voltage around 5 volts. We can even increase the switching frequency, or we can just leave it like that. Just leave it like that. The detector current, so it's working in CCM. This is very good. And let me see. Okay, the time waveform, the switching between 0 and Vin. This is correct. And the current which is flowing into the capacitor is even correct. I think that if I increase the current to 50 amps, I think that I will have to increase a bit the transient, but apart from this, no. So 60 milli is enough. So now I want you to focus on the current flowing in ID1 and ID2. For now, they are the same. For now. But if I add, for instance, let us think that here there is a parasitic inductance. There is a parasitic inductance of 1 nano here. Let's run again the simulation. And now the currents are still the same. Even here, if there is a little bit of transient, the currents are still the same, but if you do zoom, you start to see that there is a different ringing, a different spike here. And so in IM1 is receiving more current than IM2, and this spike, which is higher, can be dangerous for him, and this is what you see here. So in order to prevent this, you need to add the gate resistor in both G1 and G2. This will attenuate the effect of all possible gate oscillation, and you need of course to design the gate resistor in order to dissipate the the frequency that you want. So now if you do zoom again, you see that now the balancing is far better than before. We can even increase a bit this 2 gate resistor, and I think that we have balanced the transient, the current transient of both MOSFET. As you can see, it's well balanced. And so we have solved partially the problem of the gate balancing just with adding proper gate resistors. So if you do perform a very bad layout, and here you have for instance even 10 pico, which is very very low, you are gonna have a very different current, not only in the transient but also in the steady state. Let me show you this. As you can see, the simulation is taking quite long, and now you will understand why. Come on. Okay, so now you can see that in the transient you're gonna have a very similar voltage. Very similar, because you compensate it with the gate resistor. But in the steady state, the current which are absorbing are completely different. So if you do a bad layout, you are screwed. This is the message, basically. Let us cancel this, and so let's rerun the simulation, but with the efficiency calculation, because now you want to see how much this guy is efficient. To do this, let's use the measurement state. So .meas pin avg minus v or vin times I or vin, and .meas pout avg v or v out times I of load, and .meas efficiency param p out over p in. So let us call this out, and let's call this load, And if we rerun the simulation, we should see the efficiency. The problem is that in this way, you just see the efficiency in just one point, which is 78%. I wanted to immediately calculate this, to use this in percentage, so let's multiply it times 100. But you do know that if I do lower the output current, the efficiency will change, and it will not change casually. So if you have the efficiency here, and you have the load, and the load is increasing this way, the efficiency can be something like this. And you want to see this graph. So the efficiency now has increased. And so, to do this, we need to use the dot step param list. Yes, dot step param list. Let's call this x. Start value 10 milli, 100 milliamps. It is a list, by the way, so 1 amp, 5 amps, 10 amps, 20 amps, 50 amps, and 100 amps. And let's call this parameter x. The simulation will take quite a bit, so let's cancel this, and let's cancel also this. So basically now you are confronting with a lot of things: the efficiency and also the power loss. The power loss will increase basically quadratically with your circuit, and here you have the dead time losses, the switching losses, output, the OSS, COSS losses, so all the possible losses that you can have in a switch, and also the gate resistor losses, of course. So now the simulation is quite ended, is already ended. So let's press Ctrl R and let's see let's see how this is performing, the simulation. Let us plot this at traces. So let's use first the P in minus P out, and this is the power loss of the circuit and the efficiency. And as you can see, the efficiency is like we intended it to be. I'm probably here missing the peak, okay, because this should be far more efficient, okay. So if I probably do more investigation in this area, I think that the peak should be even 90%, because if I neglect this, I think that here the spikes are giving us some bad jokes. We can try to reduce a bit the time, and we can try to investigate more on the low power area. So 1 amp, 2 amp, 3 amps, 4 amps, 5 amps, 6 amps, 7 amps, 8 amps, 9 amps, 10 amps, 20 amps, and 100 amps directly. The simulation can take quite long. We can even try to increase the duty cycle to 0.7. The back will be very stressed, less stressed than before, and we can run again the simulation. So naturally the efficiency depends on a lot of factors. It depends on the input voltage, the output voltage, so basically the duty cycle, the switching frequency, because the switching frequency affects the losses, the dynamical losses, and also the switching losses. So you can optimize the parameters on LTSPICE to have 90% of efficiency as a design, but it is not the reason of the video. The reason of the video is just to make you see the imbalance, the problem of the current flowing in IQ1 and IQ2, which are basically unbalanced. So after the simulation, this video will end. Let us wait just a little bit. It is almost ended. Sorry for the long video, but I think that this was an important video to show. And now we have almost finished, so Ctrl L, and the efficiency has reached 95%. Yes. Neglect this bug. This is basically a bug. Yes, this is a bug. Because you don't want. This is a bug. Okay. So neglect this. You don't want to switch with this value here. It is stupid. It is very stupid to use a converter in this way. It is very stupid. Very, very stupid. But we can still plot this without rerunning the simulation. We can still plot this, and we can neglect. I think that we can put just left 1 amp and right 10. I think that we will still skip that bug. Add traces efficiency. Yes, this is basically what we are expecting. But if you put the milli, it starts to become ridiculous. No. This is just a bug. This is just a bug. You can't have 220% as efficiency. But this is the way. Okay. So if you do skip that bug, now I will show you. Maybe let me put just 0.8 amp if you just want to see something less efficient, but this is, by the way, already the efficiency curve. I know that it should be like this in most converter, because here you have a DCM, very low current operation, and you will never use the converter in this area, by the way. So you just see the curve which goes from there to there. If you are just a little bit patient, I will show you again this. But I think that you get the picture. Okay, so this is the last simulation, I will promise you. Come on! No, sorry, maybe it was not a bug. Sorry. No, it was not a bug. In DCM you have more oscillation, and the transient of 60 milli is probably not enough, so there was some kind of oscillation like this. It was an oscillating behavior. Probably, so it was not a bug. Okay. No, it wasn't a bug. Okay. So you have 95% of efficiency, and then it starts to decrease. a traces efficiency, and that's it. 97% of efficiency, and then it decreases. As I said before, in my opinion, it was not a bug. So if you put here 10 milli, I think, and you skip it, and in the you see all the transient. Stop time 10 milli. I think that he will go in an unstable condition and will oscillate forever. That's my theory. That's my theory. The oscillation it was for 10 milli, maybe? The bug was for 10 milli? No. So it was even... so I don't understand why there was... so here I have 70 milliwatt. Ah. So there was a problem here. And yes, the problem is that the current here is very, very noisy. And it's bad. And it's very bad. So it is not the output voltage, but it's the two switches which are making all the problems here. Thank you for attention, guys, and see you in the next video.